So, Jai Hind everyone. In this lecture, I am going to discuss about the state transition matrix and differential equations of and its solutions, and I will also discuss about the transfer functions. So, this topic is related to the subject control system for electronics and communication engineering 6. So, first of all, I will discuss relationship between state equation and transfer function. So, as we know that x dot is equal to axt plus but is the state equation and y is equal to cxt plus dut is the output equation. So, what we have to do, we have to find the transfer function. For finding the transfer function, I have to find the output upon input. What is the transfer function? Transfer function is nothing but the ratio of Laplace transform of output to the Laplace transform of input. So, here output is y and input is u. So, we have to find the value of ys upon us by considering all initial conditions 0. So, here first of all what will I do? I will take the Laplace transform of equation 1 for finding the value of ys by us. There are two equations, basically there are two equations 1 and 2. One is a state equation and another is output equation. So, for finding the value of ys and us, I will use ys by us, I will use both these two equations. So, first of all I will find the Laplace transform of equation 1 and by considering initial conditions 0. So, what will I get? I will get Sxs by taking the Laplace transform of equation 1. Sxs is equal to Axs plus Bus. I will write here in terms of I will find the value of xs in terms of us. So, here you will get Si minus Axs is equal to Bus and xs is nothing but Si minus A inverse B into Us. Now, you can put the value of Us into equation 2 because you have to find the value of Ys by Us. So, what will I do? I will again take the Laplace transform of equation 2. So, what will I get? I will get here Ys is equal to Cxs plus Dus. What will Ys is equal to C, Xs is nothing but Si minus A inverse Bus. So, Si minus A inverse Bus plus Dus. So, what will be the value of Ys? Ys is nothing but Si minus A inverse B plus Dus. So, what will be the transfer function? Transfer function will be Ys by Us is equal to C Si minus A inverse B plus D. Now, I am going to take an example for finding the transfer function. So, here the matrices are given, a value of A, B and C is given to you, you have to find the value of transfer function. So, for finding the transfer function, what will I do? First of all, I will find the value of Si minus A inverse. For finding the value of Si minus A inverse, first of all, you have to find the value of Si minus A, you will define Si minus A, after that you can find the value of Si minus A inverse. So, for finding the value of Si minus A inverse is nothing but adjoint of Si minus A upon mod of Si minus A. So, Si minus A is equal to S, here I have to write I is 2 cross 2 matrix with 1 0 and 0 1 minus A is minus 2 comma minus 2 1 0 minus 1 0 minus 3. So, what will you get? S plus 2 minus 1 0 S plus 3. Mod of Si minus A is equal to S plus 2 into S plus 3 plus 1. So, here Si minus A inverse will be equal to S plus adjoint of Si minus A. You will find the value of adjoint Si minus A by using this Si minus A. By using this Si minus A, you will find the value of adjoint Si minus A, that will be S plus 3 0 minus 1 S plus 2. Mod of Si minus A I have already find here. So, S plus 2 S plus 3. Now, you have to find Ys by Us. This is Si minus A inverse B plus D. So, how will you find? Si minus C is nothing but 1 1. So, you will write here 1 1 S plus 3 minus 1 0 S plus 2 upon S plus 2 S plus 3 and the value of B is 0 1. So, after solving this you will get 1 1 1 by s plus 2. How will you get this value? 1 by s plus 2. 1 s plus 2 upon s plus 2 s plus 3. So after solving this, you will get s plus 3 upon s plus 2 s plus 3, and this will be equal to 1 by s plus 2. So in this way, we have find the value of C Si minus A inverse B. The value of D is not given, so I will consider here 0. So the transfer function will be 1 upon S plus 2 for these matrices, or you can say for the given state variables. Now coming to the solution of state equations. So the for time varying system, the state equation is x dot t is equal to axt plus but. We can categorize this equation in two categories. One is homogeneous state equation and another is non-homogeneous state equation. So the equation is said to be homogeneous if A is a constant matrix and U is 0 vector. It means input is 0. It represents the free response of the system. The equation is said to be non-homogeneous if A is a constant matrix and U is a non-zero vector. So in this way, we can find the solution of state equation in these two categories. So first of all, I will consider solution of homogeneous state equation. In the homogeneous case, ut will be 0. So the state equation will become x dot t is equal to axt. So for finding what I want here, I want to find the value of xt. So what will I do? First I will take the Laplace transform of the state equation. After that I will take the inverse Laplace for finding a value of xt. So here you can say by taking the Laplace transform, this equation will become sxs minus x0 is equal to axs. So what will you get? Si minus axs is equal to x0. So xs is equal to si minus a inverse x0. xs is equal to phi s x0. Phi s is nothing but resolvent matrix and it is equal to si minus a inverse. So in this way we can find the value of xs. So what will be the value of xt? You can take the inverse Laplace of this equation. Xs is equal to phi s x0. By taking the inverse Laplace, you will get xt is equal to phi t into x0. This phi t is nothing but e power at, and this is nothing but phi s is equal to, you can get the value of phi s from here. Si minus a inverse is equal to 1 by s. I have taken s common from here. So you will take s inverse 1 by s I minus a by s. So by expanding this, you will get here 1 by s I plus a by s, a square by s square plus a square by s cube, a cube by s cube, so on. So in this way you can define the value of phi t is equal to I plus a t plus a square t square plus a 2 a square t square by factorial 2. This is nothing but the expression for e ki power at. E ki power x is equal to 1 plus x square by factorial 2 plus x x cube by factorial 3 and so on. So here this is nothing but phi t is nothing but e power at, where phi t is given by this equation 3. If phi t is known, it is possible to transit from x0 to xt. So phi t is called the state transition matrix. So in this way, in case of homogeneous solution, we can find the value of state transition matrix by considering input vector ut 0. What is state transition matrix? A state transition matrix is defined as the transition of a state from initial time t is equal to 0 to any time t or final time tf when the inputs are 0. It is the response due to the initial vector x0. It is dependent on the initial state vector and not the input. It is called as zero input response since input is 0. and it is called as it is also known as free response of the system, since response is excited by the initial conditions only, because input is 0 and we have considered only initial conditions for exciting the response. Now coming to the properties of this state transition machine. This is not the state transition machine, this is the state transition matrix basically. So I have find here phi t is the state transition matrix. Phi t is equal to I plus at plus a square t square plus a cube t cube by factorial 3. I have shown in this equation 3. So here phi t is equal to e ki power at. So phi 0 will be equal to 1. I have to write here in terms of matrix, or you can use the equation 3 for finding the value of phi t. From here, this equation is phi t is equal to I plus at plus a square t square plus a cube t cube by factorial 3. So here by putting t is equal to 0, you will get only I. So if we put t is equal to 0, then phi 0 will be equal to I. Phi inverse t is equal to phi minus t. You can put here phi inverse t e ki power minus at, it will become e power minus at, and it is also e at minus 1. So it will be phi inverse t will be equal to phi minus t. Similarly, rule 3 or properties 3, phi t2 minus t1 is into phi t1 minus t naught is equal to phi t2 minus t1. So you can put here t2 minus t1 e ki power a t2 minus t1 e ki power a t1 minus t naught. So what will you get here? E ki power a t2 minus e ki power a t1 e ki power a t1 e ki power minus a t naught. So t2 and t1 minus a t1 and plus a t1 will be cancelled out, and you will get here, what will you get? You will get here e ki power a t2 minus t naught. Phi t ki power m is equal to phi mt, where m is the positive integer. So what will be equal to phi t ki power m? E ki power at ki power m is nothing but e m at, and this will give phi mt. So these are the properties of this state transition matrix. Now coming to the solution of non-homogeneous state equation. So here in this case I will consider this input ut, and by considering this input ut, I will get here, I will consider, first of all you will consider state transition matrix x dot t is equal to axt plus but. So by taking the Laplace transform, you will get here s xs minus x0 is equal to axs plus bus. So xs is si minus axs is equal to x0 plus bus. So by taking the inverse Laplace of this equation, I will get the value of xt. So xt will be equal to Laplace inverse of si minus a inverse x0 plus Laplace inverse of si minus a inverse bus. So what will be the value of this? L inverse si minus a inverse is nothing but e ki power at. So I have written here e ki power at xt is equal to e ki power at x0 plus L inverse phi s. This is nothing but phi s, because I cannot write here L inverse si minus a inverse bus. So you can write here L inverse si minus a inverse is nothing but phi s. So this is the whole function. So I will write here phi s bus. So value of xt, the solution of the state equation in non-homogeneous case will be xt is equal to phi t x0 plus Laplace inverse phi s bus. So in this way you can find the value of xt. Now I have considered this homogeneous, I have discussed this solution of state equation in homogeneous and non-homogeneous case. So now I am going to discuss the next topic, that is controllability and observability. So the concept of controllability and observability was introduced by the Kalman. It is also known as Kalman's test. So if the system states transfer from any initial state xt naught to any other desired state xtf in a specified finite time by control vector ut, then the system is said to be completely controllable if every state variable of the process can be controlled to reach a certain objective in finite time by some unconstrained control ut. So if any one of the state variable is independent of the control input ut, there would be no way of driving this particular state variable. So if there is no connection between the certain state and input, the state is not controllable. You can see from here this figure that u is not connected to xt. So you can directly say by seeing the signal flow graph or by seeing this figure that this state x2 is not controllable. Now what is the condition for what is the condition for testing the controllability? The condition for testing the controllability is q is equal to BAB this. That is, determinant of this q matrix should be non-zero. If it is not, if it is zero, then system is not controllable. Then system is not controllable. Let us take an example for checking the testing the controllability of the system. So here the state equations are given. X1 dot x2 dot is equal to 3024 x1 x2 01 u. So A is equal to 3204, B is equal to 01. So for checking the controllability, we have to use this equation. Q is equal to B A B up to a power n minus 1 B. So I have to find the value of, I have to find the rank of this matrix. So matrix will be equal to 0 0 1 4. So there are after solving this, the value of this is given to you. BAB, B is already given, B is 0 1, B is 0 1, value of AB will be equal to 0 4, so I have written here 0 4. Since the matrix is singular, the system is not controllable. So since the matrix is singular, the system is not controllable. Now coming to the observability. A system is completely observable if every state variable of the system affects some of the output. The system is called observable if every state xt0 can be determined from the observation of yt over a finite time interval. Every state affects every element of the output vector. If any state of a system cannot be observed from measurements, it is called unobservable. So from the following figure, it is clear that the state x2 is not connected, state x2 is not connected to the output. Therefore, the state x2 is called. Now what will, how will you test the controllability? This is the Kalman test for the checking the controllability of the system. Again, the state equation is given to you and output equation is cxt plus dut. So it is completely observable if and only if the following combined matrix is x is ct, at ct is at ki power n minus 1 ct follows the, if the given system follows the condition of this observability. So in this way you can check the controllability and observability for the given system, and by using these Kalman test we can find the, we can check or we can test the controllability and observability of any system given in the state variable matrix, state variable systems.